Two-sum. Did you know the two-sum problem is one of the most frequently asked questions in interviews at companies like Google, Amazon, and Meta? It's a classic from the Pattern Mastery 100 list, and over 30% of candidates stumble here, not because it's hard, but because it tests how you think under pressure. If you can master two-sum, you'll unlock a pattern used in dozens of top tech interview questions. So, let's crack it together. Let's break down the two-sum problem. We're given an array of integers called nums and a target integer called target. Our job is to find the indices of two numbers in nums that add up exactly to target. Each input will have exactly one solution, and we can't use the same element twice. Let's assess what's tricky here. A brute force solution would check every pair, O(n) squared time complexity. That's too slow for big arrays. We need something faster. Here's a key insight. As we scan the array, we can use a hash map to record the numbers we've seen so far and instantly check if the complement, target minus current number, is already present. That gives us O(n) time and O(n) space. Now, let's structure our approach. We'll create an empty dictionary to store numbers and their indices. As we loop through the array, for each number, we'll compute its complement. If that complement is already in the dictionary, we return the pair of indices. If not, we add the current number and its index to the dictionary.
Let's try to implement it using solution 1. We begin by defining our solution class. This is the container that holds the method we are about to walk through. Then we declare the two-sum method. It receives two things: nums, the list of numbers we will search through, and target, the sum we are trying to achieve using two numbers from the list. Next, we start our outer loop. Here, I moves from the start of the array to the end, checking one number at a time. This loop runs in O(n) time. For each I, we start an inner loop with index j beginning at I+1. This ensures that we only compare each pair once, and we never pair a number with itself. Together, the two loops give this solution a time complexity of O(n) squared. Inside the inner loop, we check whether the numbers at positions I and j add up exactly to the target. If they do, we have found the correct pair, and once we find that matching pair, we immediately return their indices inside a new array. There is no need to continue searching. The answer has been found. After both loops finish, if no pair adds up to the target, we return an empty array. This signals that no valid solution exists. And that is how this algorithm works. It loops through each number, then checks every possible partner for a match, and returns the indices as soon as it finds the pair that sums to the target. Efficient. Simple. Clean. Check. Let us run through this two-sum test case and confirm why the output makes perfect sense. Input: nums equals 2, 7, 11, 15. Target equals 9. As the algorithm processes the array, at index 0, the number is 2. To reach the target 9, we need 7. We keep going. At index 1, the number is 7. This is exactly what we were waiting for, because 9 minus 2 equals 7. The pair 2 and 7 adds up to the target. Their indices are 0, 1. The output is 0, 1. This matches the expected 0, 1. The solution correctly identifies the two numbers that sum to the target. Now let us try another implement approach using solution 2. We begin by defining the solution class. This is the container that will hold our method. Then we declare the two-sum method. It receives an array of integers and a target value we want two numbers to add up to. Next, we create a hash map called M. This map remembers the numbers we have seen so far, storing each number as a key and its index as a value. Lookups in a hash map run in constant time on average. From there, we start looping through the array one index at a time. Since each element is visited once, this loop runs in O(n) time. Inside the loop, we calculate the complement C. This is the number we need to pair with nums at index I in order to reach the target. For example, if the target is 10 and the current number is 6, the complement is 4. Then we check if that complement has already been seen earlier in the array. If it has, that means we have found the two numbers that add up to the target. The complement stored in the map and the current number, so we immediately return their indices. If the complement is not in the map yet, we store the current number and its index. This allows future values to check against it quickly. This closes the loop. After scanning all numbers, we either return early with a valid pair or move to the final step. And if we finish the loop without finding any valid pair, we return an empty array to indicate that no solution exists. And that is how this algorithm works. It builds a hash map on the fly as it scans the list. Then it checks each new number's complement in constant time to detect the correct pair immediately. Efficient. Simple. Clean. Check. Here is the verification for this two-sum test case. Input. Nums equals 3, 2, 4. Target equals 6. We want to find two numbers that add up to the target. Index 0 has value 3. To reach 6, we need another 3. That has not appeared yet, so we store it and move on. Index 1 has value 2. To reach 6, we need 4. Not seen yet, so we continue. Index 2 has value 4. Now we check the complement of 4, which is 2. We have already seen 2 at index 1, so the correct indices are 1, 2. The output is 1, 2. This matches the expected 1, 2. The algorithm correctly identifies the pair that sums to the target.
Let's have a quick recap. Breakdown recap. In this challenge, we were given a list of numbers and a target value, and our goal was to find the two numbers that add up exactly to that target. It's one of the simplest yet most iconic interview problems because it tests how you connect logic with precision, not just how you write code. Assess recap. We explored different ways to solve it and saw that brute force, while straightforward, is too slow for large inputs. The real breakthrough came from realizing we could use a hash map to keep track of numbers we've already seen and quickly check for their complements. That insight transformed the problem from quadratic time to linear time. Structure recap. Our logical plan was simple. Loop through the numbers, calculate each number's complement, and see if that complement has already appeared. If it has, we found our pair. If not, we store the current number and keep going. A clean, step-by-step flow built on efficient lookups. Implement recap. As we coded, the process came to life exactly as planned. We tracked numbers in real time, checked complements on the fly, and watched how the logic naturally identified the correct pair. It was a perfect example of turning algorithmic reasoning into an elegant, working solution. Check recap. When we ran our test case, everything lined up. The indices, 0, 1, appeared exactly as expected. That confirmed the logic worked and that our hash map strategy performed efficiently, delivering a precise ON solution with minimal space overhead. The two-sum problem is a reminder that simplicity can hide depth. It's not about complex math, it's about using the right tools to think smarter, not harder. Once you master this pattern, you'll recognize it everywhere. A foundational skill for building faster, cleaner, and more confident solutions in every interview.